So looking at our first video in 3.6, we're going to be looking at graphs and trying to find functions to solve what our word problems are telling us. So here in this problem it says let f of x equal x squared. Okay, that's my parabola right here. Find a function a of x. So x can be the only variable in my expression for the area of the shaded triangle where the first corner must stay at the origin, right there. The second corner must be on the y-axis somewhere, and the third point is somewhere on our parabola, f of x. And they're going to keep this xy point, has to stay in quadrant 1 here. So that means I can have this triangle, and I only want to use this x to find the area. We could have this right triangle, we could have this small right triangle, but whatever x you are given right here for that point on the parabola has to be used to find my area formula. So since we're dealing with a triangle, let's look at its formula, 1/2 times base times height. So here's the base, here's my height. So right now it appears to me that my base is going to be the variable x. And my height is going to be the variable y. But wait, y is the same as f of x, so we can tell our y to be x squared. And when we go base times height, we'll have x times x squared. Multiplying those together gives me x cubed. And now here's the function that will find the area of any triangle with these conditions based on this x coordinate somewhere on that parabola in quadrant 1. All right, next example. Here we're going to use the equation of the circle x squared plus y squared equals 36, which represents this semicircle here. And any point on this semicircle, we're going to find the area of AX for our rectangle on the inside of our semicircle. So here we have a slight problem that I'm going to encounter. If my point can be over here in quadrant 2, my x could possibly be negative, and I don't want negative numbers because you can't have negative distances. So let's keep that in mind when we build our formula here. So my area of the rectangle is going to be base times height or length times width. It doesn't matter which one you use. So here's my base, here's my height. So let's just say we're working so we understand this negative number concept. Let's say my x and y is over here. Well, I can see that the height is going to be the y coordinate no matter which point I choose. And my base, since it's along the x-axis, it's going to have to be x's. So I have an x distance here, and I have another x distance over here, which is the same. So these two distances are the same. Now I don't want to use -4. It's got to be a positive distance, so I should have 4 plus 4 in this particular case to give me a positive 8. So that's going to be a base of 2x. But again, like we said, we have to guarantee that that is going to be a positive value. So if I was looking at this as my point right here is x comma y, my x would be negative, and I don't want to have a base that's -8. So to guarantee a positive value, we're going to put absolute values bars around the x's because your x's could be negative. They said you can go anywhere on the semicircle. The y you don't have to worry about. We have only positive y's. So here's my formula so far, but again, we don't want y in my function because I'm only allowed x's. So I need, let's see, I need that circle equation, and I'm going to need to solve that for y. So I'm going to subtract over the x squared, take the square root of both sides, and that's going to give me y equals the square root of 36 minus x squared. And I notice I did not put the plus or minus on there because in my semicircle, all my y coordinates are positive. So we'll just leave this as a positive. So we'll transfer the square root of 36 minus x squared up in our formula, and there's my function. Now, if they give us another question, for example, what x-coordinate in quadrant 1 will maximize the area? Okay, so if I'm going to quadrant 1, all my x's are going to be positive. I don't need the absolute value bars. What I need to do is I need to graph this function and look for its relative max somewhere between an x-coordinate of 0 to an x-coordinate of 6. So any point here gives me an x from 0 to 6. So I need to bring my calculator into the game. Here we go. Oh, you would have to do that. So let's see, I'll just try to remember it here. So y equals, we don't need the absolute value bar, so it's 2x times second square root. You don't actually have to hit the multiplication symbol. It'll be implied multiplying there. 36 minus x squared. Now, before I graph this, remember, it said we're only going to be in quadrant 1. So I'm going to go change my window so my x min will be 0. My x max will be 6. Now, the y coordinate is going to be my actual area. So what I'm going to do is I'm going to change my y min to 0 because I can't have negative area. My y max, well, thinking about the graph there, looking at your graph paper, I'm just going to overachieve. -6 to +6 is a base of 12. The height is 6. 6 times 12 is 72. So I'm going to make my y max 70, just to be on the safe side. If you want to change your y scale so you don't have 70 tick marks to look at, you can count by tens. That's optional. Now we graph it. Okay, so here's my curve. I can clearly see it's increasing and changing to decreasing somewhere in this area, which is giving me a relative max. So I'm going to go to my second trace, my calculation window, ask for a maximum, number 4. Now that looks like a good point to start with. We'll start there with x being 3. We'll just hit enter. And I'm going to choose, that's 4, that's 5. I'm going to choose a 5. I can clearly see that 5 is definitely to the right of where the relative max is. And on the guess, you can just hit enter. And so here is the x-coordinate that you want to generate the biggest possible area for the rectangle, which in this case is 36 square units. So this is the maximum area. That's the biggest area. And that happens when you're at 4.242673. If this was in my math lab, you would just round it to whatever decimal they ask you to. All right, that ends this 2 examples.